Namaste and a very good evening to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about how to build a deep learning model using RStudio. Even before I demonstrate how to build a deep learning model using RStudio, may I request you to subscribe to my channel, also like and share my videos. Let's begin by asking a simple question as to what is the first step that we need to perform to build a deep learning model. There are two very important libraries which are called as TensorFlow and Keras. The first thing that we need to do is install these two packages in RStudio. So let me go ahead and install two important packages, namely TensorFlow and Keras in RStudio. You can see here in the first line, I'm giving a comment which says install the packages. And in the second line, I'm specifying the name of the package that I need to install. What exactly is TensorFlow? TensorFlow is a free and open source library for machine learning and artificial intelligence. It was developed by Google to train deep learning models. The next question is, what exactly do we mean by Keras? Keras is a high-level deep learning API which was developed by Google for implementing neural network. I've already installed these packages in RStudio, so I will not be reinstalling these two packages. Let me now go ahead and call the library TensorFlow and call the library Keras. So at this stage, what I've done is I've installed the two important packages for deep learning, TensorFlow and Keras. In the next step, what I'll be doing is I will be loading the dataset that I'll be using for this particular video. So in line number 9, I will be loading what is called as the MNIST dataset. So this is the command that we can use to load the dataset. When you install the Keras library, by default, the MNIST package would come in. You don't need to separately import this particular package. You can use the dataset underscore MNIST of command to load the dataset. One important point here is, what exactly is this MNIST database? The MNIST database stands for Modified National Institute of Standards and Technology Database. I repeat, MNIST stands for Modified National Institute of Standards and Technology Database. This is a large database of handwritten digits that is commonly used for training various image processing systems. The database is also widely used for training and testing in the field of machine learning. Let me go ahead and load this particular dataset. At this stage, I have created what is called as the MNIST object, which consists of the handwritten images of 70,000 different digits. In the next step, what I'll be doing is I will be creating a split in the dataset. I'll have to create what is called as the training dataset as well as the testing dataset. Remember, we split the data into training and test. The training data is fed into the machine learning model, which will learn certain patterns and characteristics from the data. This model will then generate predictions on the test data, and by comparing the actual values with that of the predicted values for the test data, we will be able to assess the performance of the model. So from the base data of MNIST, I will be creating 4 new objects. What are these 4 new objects? Let me quickly show you what are the 4 objects that I will be creating. In line number 12, you can see the 4 objects that I am going to create. The first is x_train. Then I'll be creating x_test, y_train, and y_test. X_train will consist of the independent variables which are part of the training dataset. X_test will consist of the independent variables for the test dataset. Y_train will consist of the handwritten images of the different digits. Last but not the least, Y_test will consist of the handwritten images in the test data set. So we have created 4 different objects at this stage. You can look at the console window, x_train, x_test, y_train, and y_test. Y_train and y_test are the dependent variables. X_train and x_test are the independent variables. Let's further explore the data. We will very quickly check the sample size and the dimension of the data. So in line number 18, what I'll be doing is I'll be writing a simple code to evaluate the sample size of the training as well as the test data. There is a simple command which is called as the structure command. Let's go ahead and execute the structure command on x_train. You can see here, when you execute the structure command, it shows 3 dimensions. The first one says that there are 60,000 images in the training dataset. I repeat, there are 60,000 images in the training dataset. The second dimension here represents the height of each and every image. The last dimension here represents the width of each and every image. So overall, we have 60,000 images where each image has a dimension of 28 by 28 pixel grayscale images. Let's now quickly look at the dimension of the test data. We go ahead and execute this particular command. Here you can see we have 10,000 images in the test data. Each image has a height whose size is 28 and the width whose size is 28 again. Let me quickly adjust the font size in R. To adjust the font size, you can quickly go to Tools. The last option here is Global Options. This will open up a new dialog box. The fourth option from the left side is Appearance. So 24 may be slightly on the higher side. Let me check 18. 18 is still okay. It is visible. Let me apply 18 font size and click on OK. Now, what we have done so far is a bit of exploratory data analysis. The next thing that we need to do is we will investigate specifically how does the handwritten digit of 5 appear. I repeat, how does the handwritten digit of 5 appear? So let's look at line number 22. Here, what I'm doing is I'm specifically selecting 9 digits. I'm specifying the position of the digit 5, namely 1. Then you have 12. In the 36th position, again, you have the handwritten digit of 5. Like this, I'm specifying the position where the handwritten digit of 5 is. present. Let me create an object called as A. Then we are going to use another function which is called as PAR of MF row equals C of 3, 3. We go ahead and execute this particular command. What does this command do? This command in R sets the plotting layout to a 3 by 3 grid. I repeat, this command in R sets the plotting layout to a 3 by 3 grid. This allows 9 plots to be displayed simultaneously. Let me now go ahead and execute line number 25. It says there's an error. To debug this particular error, I can simply type PAR of MAR equals C of 1, 1, 1, 1. I'm just adjusting the margins so that we can accommodate the 9 images. You can see here, once I execute this particular command, you will be able to see the 9 images of the handwritten digit 5. Different people have different handwriting. Somebody may write 5 like this. Another individual can write 5 in a different way. The third person can write 5 in a totally different way. You can see here, these are the 9 images of 5. You and I as human beings can recognize that this is the digit 5. Question is, can we build a deep learning model which can clearly recognize that each of these digits represent 5? And what is the level of accuracy of such a model? My first impression is that when you look at this particular image, that is the 7th image, the model might struggle to recognize this as 5. This might be misclassified as either a 3 or a 1. Let's go ahead and build the model and then check the performance of the model. We've just now seen 9 different samples of the handwritten digit 5. Let's now explore the dependent variable. As you can see here, to explore the dependent variable, I'm simply calling the object y_train. Let me go ahead and execute this particular command. Once you execute this particular command, you can see this is the output that is being displayed. Let me quickly show you what we have here. These are some of the digits. The first image has a digit of 5. Then you have 0. The third image has a digit of 4. The rest of the digits are also being shown here, like 1, 9, 2, so on and so forth. Just as we took a peek into the object y_train, let me again go ahead and investigate what is there in y_test. I've executed line number 31. You can see here the different handwritten digits in the test data. The first image here is 7. Then we have 2, followed by 1, so on and so forth. This helps me get a perspective as to what is present in the dependent variable. Next, after exploring the dependent variable, it is time for us to plot the images and see how do the first 9 images appear. So in line number 33, I will be plotting some of these images. You're already familiar with this particular function, PAR of MF row equals C of 3, 3. What does this do? As I told you earlier, this is a command in R which sets the plotting layout to a 3 by 3 grid. This allows 9 plots to be displayed simultaneously. Next, let me use a for loop to display the 9 images which we have in mind. As you can see here, these are the 9 images that we have. We earlier saw only the digit 5. Now what we see is the first image is 5, second is 0, the third image is 4, then we have 1, 9, 2, 1 here, 3, and 1. We'd like to feed this and build a model. You've seen a sample of 9 different images. The next step would be to see the handwritten digit in the data. How do we do this? In line number 38, what we are doing is we are pulling out the second image. The second image is that of 0. Instead of second image, let me change this to the third image, which is 4. You can see here, there is an object of 4 here. There's a digit of 4 rather. We'd like to be able to identify the digit 4 in the data. But before I execute this, you can see here, the font size is on the larger side. So I like to reduce the font size so that it's a lot easier for me to display the entire image. How do I do this? I can go to the tools option. The last of the item here is global options. This will open up a dialog box which is called as options. The fourth option from the top is appearance. Let me click on appearance. The current font size that I'm using is 18. Let me reduce this to 7. This is very small and it will display the contents of the image adequately. I've applied this and clicked on OK. Let me see how does the digit 4 appear. Let me maximize the console window. You can see here, this is how the digit 4 appears. I know it's a bit difficult to spot this. Let me try and execute this once again. You can see here, this is how the digit 4 appears. Let me now experiment by taking a different image. We can go ahead and pull out the 5th image. Execute this in the console window. You can see here, the 5th image is the handwritten digit of 9. So this is how 9 would be appearing. This was just an experiment to see how the data is arranged. I like to go back to tools once again, global options, appearances, increase the font size to 18. This is more comfortable. Apply and OK. What is the next stage in our analysis? The next stage in our analysis would be to check the frequency distribution of each and every image. We can check the frequency distribution of the train as well as the test data. You can see here, I'm using the table command to execute the frequency distribution firstly on the training data. If we go ahead and execute this, you can see here, this will give me the frequency distribution. So in the training data set, there are 5,923 images of the digit 0. Then you have 6,742 samples of the digit 1. Similarly, you have 5,958 samples of the digit 2. When you study the diagonal elements, the biggest number is 6,742. Let me check this thoroughly. 5,949. I think no number is as big as 6,742, which means that the maximum count that we have is for the handwritten digit of 1. This is the distribution as far as the training data is concerned. Let's now go ahead and execute the test data, the table command on the test data. Let's look at the frequency of each and every digit. You can see here we have 980 samples of the handwritten digit 0, 1,135 samples of the handwritten digit 1. Similarly, you have 1,032 samples of the handwritten digit 2. When you look at the diagonal elements, the biggest number is 1,135, which corresponds to 1. So the maximum number of images that we have in the test data is for the digit 1. Let's come back to the code window. So far what we have done is to check the distribution of each and every class of the dependent variable. What next? The next stage is to rescale the data. We will be normalizing the data. How do we normalize the data? To normalize the data, one easy command that you can go ahead and use would be, you can see here, we can just take the independent variables and divide it by 255. I'm going to repeat the same thing for the test data as well. What this does is it will make sure that every number will lie between 0 and 1. Remember, normalization is a very, very important step in image analysis. After normalization, what is the next thing? The next thing here after normalization is to convert the class labels to one-hot encoding. I will be converting the class to one-hot encoding. You can see here in line number 49, what I'm trying to do is convert the class labels to one-hot encoding. Please observe that the to underscore categorical of function. Why do we need this? The to underscore categorical of function is typically used in the context of classification tasks where the goal is to predict one of the several possible classes based on the input features. In this line, what we are doing is we are using the to underscore categorical function in R, which is used to convert the target variable y underscore train into a categorical variable which is suitable for training a machine learning model. The second argument 10 in this case specifies the total number of possible classes in the dataset and is used to determine the number of output categories. The function then creates a new matrix or array where each row corresponds to an instance in the original dataset and each column corresponds to a category. For each row, the value in the category column corresponding to the class label of that instance is set to 1. and all the other category values are set to 0. In other words, the function creates a one-hot encoding of the class labels. Let me go ahead and execute this particular command. So we have one hot encoded the dependent variable for the training data set as well as the testing data set. What is the next step in our analysis? Once we have one hot encoded the data set, the next step is to define the neural network architecture. Let me quickly show you the architecture of the neural network model. You can see here, this would be the architecture of the neural network model. What exactly is going on here? Let's now examine line by line as to what exactly is happening in this neural network architecture. Let's begin by looking at the first line, wherein we have written Keras underscore model underscore sequential of function, and this is being assigned to the model object. This is followed by a series of pipe operators. You can see here, these are some of the pipe operators that add layers to the model. What this does is it creates a sequential neural network model using the Keras library in R. The Keras underscore model underscore sequential of function creates an empty sequential model object, which can be used to build a feed-forward neural network with a linear stack of layers. I'd like to repeat this. The Keras underscore model underscore sequential of function creates an empty sequential model object, which can be used to build a feed-forward neural network with a linear stack of layers. Further, you can see the pipe operator. The pipe operator is used to chain together a series of layer building functions. I repeat, the pipe operator is used to chain together or link together a series of layer building functions in a compact and readable way using a technique called functional programming. Now, the first layer that is added to the model is the layer underscore flatten of layer. I repeat, the first layer is the layer underscore flatten of layer, which takes the two-dimensional input data 28 cross 28 pixel images. What this does is it flattens this into a one-dimensional array. The input shape that you see here, this is an argument which specifies the shape of the input data. In our case, the shape of the input data is 28 by 28 pixel image. The next layer that we see, which is added to the model, is a layer underscore dense layer. I repeat, the second layer that we see is layer underscore dense of layer, which is a fully connected or a dense layer that takes the flattened input data and applies a linear transformation to produce a set of 128 output values. So this will produce 128 output values. The units argument specifies the number of neurons. You can see here, this specifies the number of neurons in the layer. We have the activation function. This particular argument specifies the activation function to be used. In this case, we are using a function which is called as the ReLU activation function. The third and the final layer that is added to the model is another layer underscore dense of layer. What is happening here? Now, this particular layer takes 128 output values from the previous layer. I repeat, it is going to take 128 output values from the previous layer and produces a set of 10 output values, one for each possible class label. The activation function used in this layer is a softmax activation function, which is commonly used in classification tasks to produce a probability distribution over the possible classes. So this is what each layer in the model does. Taken together, these layers create a simple feed-forward neural network model. I repeat, when you look at this from an overall perspective, this is going to create a simple feed-forward neural network model that takes a 28 by 28 pixel image as the input, processes it through two dense layers, and produces a probability distribution over 10 possible class labels. The model can be trained on labeled data using an appropriate optimizer and loss function. Let's now go ahead and define the neural network architecture. We have successfully created the architecture for the neural network model. What is the next stage? What we have done in the defining the architecture stage would be to create the blueprint of the model. The next stage would be to compile this particular model. How do we compile the model? Let me show this in the next stage. In line number 60, we can go ahead and compile the model. You can see here what we are doing in the compilation stage is to specify three important parameters. One would be the loss function, wherein we are taking the categorical cross entropy as the loss function. The optimizer that we would be using would be optimizer underscore RMS prop. Finally, the metrics that we would be interested in would be the accuracy metric. Let me go ahead, select this particular code and execute. We have successfully compiled the model. Just to recall the steps, firstly, we defined the architecture of the model. Then we compiled the model. What is the next stage? The next stage is to train the model. Let's go ahead and quickly train the neural network model. So in line number 67, what we are doing is we are trying to fit the neural network model using X underscore train and Y underscore train respectively. The number of epochs I have maintained as 10. You can experiment with either 20, 25, 50, or for that matter, even 100. The batch size here is 128, and we are using 20% for validation. We go ahead and train this particular model. You can see here the model is displaying the results. Right now, we are in the fourth epoch. Either we can look at the output, which is in the numerical form. You can see here, this is the 10th epoch. The validation accuracy here at this stage would be 97%, which is a good number. However, I'd like to show you the graph which comes along with this. You can see here, this is the graph which measures or evaluates the performance of the model. You can see here, there are two line graphs. The first would be the loss computation. In the x-axis, we have the 10 epochs. This is the first epoch, second epoch, third epoch. You can see here, this is the second graph. In the second graph, we are plotting accuracy. Do remember, in the first graph, we are plotting the loss value for both training as well as test. In the second graph, we are plotting the accuracy measure. Let me draw your attention to the first graph. Remember, the legend corresponding to blue represents the training loss, and the green represents the validation loss. In the first epoch, when I hover the mouse on top of the blue line, you can see here the training loss was maximum. It was 38%. It is quite high. Compare this to the validation loss, which was 22%. In the second epoch, the loss has reduced to 18%. So this is a good improvement. From 38% for training, it has reduced to 18%. And the third, it has further reduced to 13%. Subsequently, in each of the iteration, the loss goes on reducing. And by the time we reach the 10th epoch, you can see here, the loss is 3%. So from 40%, we have been able to reduce it to 3%. This shows that the deep learning model has learned the characteristics quite well. One important point here is that we do not usually look at the loss from the training perspective. What is important is what is the loss for the test sample. When you look at the green color line, that indicates the performance of the model on the test or the validation sample. In the first epoch, the loss value for the test was 22%. In the second, it has reduced to 15%. And in the third epoch, it has reduced to 12%. When you look at the last epoch, the loss is 9%. It is not a small achievement that we've been able to reduce the loss from approximately 22% to 9%. So this is the story as far as the loss is concerned. The general thumb rule is that the loss should go on reducing. We want to reduce the loss or the error. We don't want to maximize the loss. Let me now draw your attention to the second graph. In the x-axis, we have the 10 epochs, and in the y-axis, we have the accuracy level. Here we are plotting accuracy. In the first graph, we are plotting the loss. Let me draw your attention to the green line, which indicates the accuracy for the validation sample. The accuracy was 93% in the first epoch. It has further increased to 95% in the second. In the third one, the accuracy has jumped up to 96%. Let's look at the last epoch. You can see here the validation accuracy is 97%. What's the story as far as the training data is concerned? Here in the training data, the final accuracy that we are obtaining is 98%. 98% is a high number, so which is a good sign that the model has trained well. So the graph on accuracy and loss are really important and were informative. If you want to print the overall accuracy of the model, the final accuracy of the model, what you can do is you can run the following commands. In line number 74, you can see we are evaluating the model on the test data. Let's create the object score and compute the test loss, which is around 7.9. You can round it off and say 8%. So the test loss is 8%, and therefore the accuracy is 100 minus 8, which is approximately 100 minus 8 would be 92%. When you look at the test accuracy here, the accuracy level that we are getting is 97.7%, which is a good number. So in this exercise, what we have done is we have seen how to install the two libraries, namely TensorFlow and Keras. After installing, we looked at the MNIST dataset. We tried to explore the different handwritten digits, post which we did some feature engineering. We performed the one-hot encoding. We also rescaled the data as far as the independent variables are concerned. Next, a very, very important stage was to define the architecture of the model, which is almost like the blueprint of the neural network model. After which we compiled the model, and then we went on to train the deep learning model. Finally, we were able to evaluate the performance of the model. We got an accuracy level of 97.7% on the test data, and the loss value was 7.9%. With this, I've come to the end of today's video. In today's video, we have seen extensively how to build a deep learning model in RStudio. I thank you very much for watching this particular video. I request you to subscribe to my channel, also like and share my videos. Thank you very much. Have a great day ahead.